All right, so we begin this morning talking about some energy things. And we start today with probably the most misunderstood question and equation in all of science. Everybody loves to talk about it. Nobody knows what it means. That is, in Einstein's theory of relativity, E is equal to mc squared. Now, what does E is equal to mc squared actually mean? Well, what it means is we have E, the nuclear binding energy, equal to the mass defect, m, multiplied by the speed of light squared. That's the c squared. Now, this nuclear binding energy, this is the thing that answers the question that probably every student has had when they stop to think about it. And that is, how does a nucleus exist in the first place? You know, we understand that a nucleus exists. We have the experimental evidence to say so. But we also know about charges. And the idea that you're going to cluster together all of these positive charges in this nucleus, and the nucleus isn't going to just fall apart from Coulombic repulsions, is a thought that's crossed probably every person's mind who's actually stopped to think about it for a second. Why doesn't the nucleus just fall apart? What is holding this nucleus together? And the answer to that question is nuclear binding energy. Now, where does that nuclear binding energy come from? Well, it comes from something called mass defect. What is mass defect? Mass defect is the energy generated by converting mass into energy. Now, why isn't this something that we really have talked about much on the whole? Well, because up until this point, it really hasn't been terribly relevant. And the mass differences that we're talking about here are incredibly small. In converting from reactants to products in a chemical reaction, the mass defect associated with the energy conversion of mass puts the loss of mass on the 1/1000th of a gram kind of scale, something we would never notice. But in radioactive decay, the mass losses are actually quite significant. Because on the whole, on the nucleon level, we are talking about a considerable percentage of the actual mass of the object. And because of that, it's relatively easy to detect. So what is it? Let's kind of go back to what is mass defect. Okay. Okay, so let's get away from the tables here. I realized I just didn't put in anything until we got to the actual problem here. So let's ignore this graph for a second. Let's just talk about what mass defect is. So we're building a nucleus. Now, in that nucleus, we have protons and we have neutrons, right? The atomic mass of a proton and the atomic mass of a neutron just slightly over 1 AMU. So when we build this out, what we will find is that the difference between the individual subatomic particles and their masses versus the mass of the nucleus that they create is different from each other. So let's just jump to this practice problem here. If I have 4 protons and the atomic mass of a proton is 1.0073 AMUs. Well, if this is the case, then the starting materials that I'm dealing with are 4.0292 AMUs. I want to convert this into grams. We would get 6.6908 times 10 to the negative 24th grams. So this is my starting material. The alpha particle and the 2 positrons would have a mass equivalent to that of helium. So 4.003 AMUs. If I convert that to grams, (4.003) divided by Avogadro's number we get 6.647 times 10 to the negative 24th grams. So here are my reactants, and here are my products. And I can see that the two masses that I have are in fact different from each other. Not gigantically different from each other, but definitely different from each other. The difference between these two, so if I subtract them, I would get the delta M, or the mass defect. (6.6908 times 10 to the negative 24th grams minus 6.647 times 10 to the negative 24th grams we get 4.38 times 10 to the negative 26th grams, which would be 4.38 times 10 to the negative 29th kilograms. Now, that doesn't sound like a ton of mass. And if we plug that into the Einstein equation, 4.38 times 10 to the negative 29th kilograms multiplied by the speed of light, 3 times 10 to the 8th meters per second squared, we get 3.94 times 10 to the negative 9th joules, which again doesn't sound like a ton of energy. That's the number of joules for one conversion of protons into this alpha particle and two positrons. If we did this on a molar scale, then we're talking about 2.37 times 10 to the 15th joules per mole. And we would certainly notice that difference. On the molar scale, we're talking about, see, million, billion, trillion, quadrillion, 2 quadrillion joules per mole. That's more energetic than any reaction we've done this entire year. So this is what the Einstein equation is doing. So why does the nucleus stay together? Well, the reason it stays together is because when we combine these raw materials, these protons and neutrons, into a nucleus, a significant amount of energy is released in that process. And so it would require that much energy input to break the nucleus apart and get back our protons. And so with any kind of nuclear reaction, this is ultimately what you are doing. Is we're looking at the masses of the products minus the masses of the reactants. Now, we did reactant minus product here. it really doesn't matter. It's all about what direction the energy is going. Again, here, sign indicates only direction, not magnitude. So if I had done products minus reactants, this would have been negative, meaning that this amount of energy was released as that alpha particle is being formed. It would take this amount of energy to break apart the alpha particle and get the protons back. Now, let's go back to this graph. Binding energy is a factor that does change on a atom to atom, nucleon to nucleon kind of basis. And what we see is that, generally speaking, our lighter elements will work their way towards stability. The most stable isotope that exists is iron. Iron 56 is the most stable, and it is for this reason that some chemists will say that in the end everything strives to be iron. If you look at nucleosynthesis in stars, most stars, like our star, the sun, start off as a hydrogen burning substance, a white star. Over time, as they run out of hydrogen, they start to burn through helium. They turn into red stars. And what we'll see is that at the core of that process, the core of the star will start to turn into iron. If it makes it that far, if it doesn't go to supernova and die a spectacular star death in between. So on this side of iron, what we see is a tendency for elements to fuse together, especially in nucleosynthetic kinds of relationships in stars. And on this side of iron, we tend to see things that are going to participate in fission, where they break apart as they're trying to gain stability to ultimately get to that most stable iron isotope. So binding energy is not something that is a constant flat across the board for all atoms and for all elements. It does vary and it does change. And ultimately, iron 56 is kind of considered the ideal goal. Now, that ideal goal is something that an individual nucleus might achieve over the course of millions and billions of years, and certainly not in any kind of fast process. Most of the elements and isotopes that are listed here, these are all stable forms. And the only reason they would fuse together is if the conditions were absolutely correct for it to do so. You're not going to see hydrogen fusing together randomly in the atmosphere here. The conditions aren't right. We need high pressure and usually high temperature to do it. So we move on to talking about nuclear reactions just kind of in general. And what we'll see often here is the role of neutrons. Neutrons are important to nuclear processes because with neutrons, we can modify the existing nucleal structure, but do so without interrupting and adding to the general repulsion inside of the nucleus. If I were to try to add protons to the nucleus, it would be difficult. The reason it would be difficult is because protons repel other protons. And so that increased in Coulombic repulsion would severely hamper the stability of the nucleus that I'm trying to create. Similarly speaking, if I have positively charged nuclei, which all nuclei are, there's a tendency that the nuclei themselves will repel each other. Again, this is Coulombic repulsion. Positive charges do not attract each other, they repel each other. And if we're going to overcome Coulombic repulsion, we need to introduce enough energy to make that kind of repulsion overcome. And so if we were going to do any kind of bringing together of nuclei, we need to raise the temperature inside of that reaction vessel to roughly 100 million Kelvin. So, as you might imagine, this is not something that most objects on Earth are capable of handling. So, where can we do nuclear chemistry then? Well, one thing that was discovered, and so if we go back to our kind of beginnings here in early 20th century science, we end up in 1930s Europe, which is a dangerous place to be. 1939, we are talking about full on in the middle of the Nazi overtake of Germany. We are fully in the middle of World War II in Europe. The United States has not been involved yet, but we're about 2+ years from that taking place. But what we find in that in a laboratory in Germany, Hahn and Strassmann are working with uranium, and they're directing neutrons at this piece of uranium. And what they're discovering is that as this uranium is being bombarded, they're finding radioactivity with signatures that are more like barium than uranium. If you look at your periodic table, uranium is element number 92, barium is element number 56. So it's not like we just kind of lost one along the way. We're talking about a difference here of 36 in terms of atomic number. So something drastic is happening to this uranium. And the drastic thing that's happening to the uranium is that it is undergoing a process known as nuclear fission. So if you take this, otherwise, we won't use the word stable because it's not accurate. But we've got this uranium-235, which is, let's call it metastable. It's radioactive, but it's not, half-life of 1.5 seconds kind of radioactive. It's stable enough that we can find it in uranium rock and ore in the ground, and the majority of the sample is uranium-235. So we know it decays, but we also know it decays relatively slowly to the point where we can actually measure and quantify the amount that's there. But we take this uranium and we bombard it with a neutron, and in the process, that neutron gets absorbed by the uranium and turns into uranium-236. Now, uranium-236 is not the stable kind of thing that uranium-235 is. The net result is the lack of stability in that uranium causes the uranium to split. And that's what is called fission. Fission is the nuclear splitting of an unstable nucleus. In the process, their uranium turns into an isotope of barium. So there's my barium that the German scientists were discovering. And we get an isotope of krypton, krypton 92. Now, neither of these two particular isotopes are terribly stable on their own. Again, barium's atomic mass is 137.33. So we would expect most of the barium to be barium 137. And for krypton's molar mass is 83.8. So the majority of krypton we expect to be 84. This is 92. So in both cases, we have a whole bunch of extra neutrons, meaning that this barium and this krypton are going to undergo further decays from here. But what's interesting about this process also is that these neutrons are ejected from the process as well. And as you can imagine, this breaking apart, we just talked about binding energy. Well, if we are creating a lack of stability, where's that binding energy going? It's going outward. So not only are we creating these two new nuclei, we're creating these three neutrons and we're creating them with a ton of energy. What's to prevent these neutrons from going out and attacking other uranium-235 atoms and having them do the same thing? Well, when that happens, we have what is called a chain reaction. One reaction begets another reaction, which begets another reaction, which begets another reaction. And pretty soon we've got a whole bunch of energy and a whole bunch of radioactive material all floating around all at once. So Meitner and Frisch, two more German physicists, explained the results of Hahn and Strassmann in 1940. They go ahead and publish their findings in international journals. And now we have an idea of how to initiate fission reactions. This leads to 1940 comes the beginning of the Manhattan Project here in the United States. The net result of the findings of that paper from Germany tell us that, okay, well, hold on a second. If we harness this particular idea into a more prominent weapon, the results of this weapon would be quite devastating. So, out of fears that the Germans would beat us to this, the Manhattan Project was developed because, let's face it, German physicists were pretty damn good. Fast forward 15 years, the number one export out of Germany during the Cold War are scientists. Some of them go over to the Soviet Union to develop the space program there. Some of them come over here to develop our space program, and kind of the rest is history there. So these fears were not unfounded. You look at people like Otto von Braun, who developed the Saturn V rocket for NASA, the rocket that ultimately allowed us to go to the moon. he was working in a Nazi laboratory before he came over here. So it's not exactly poor thinking on the part of our government or on any other government for that matter to try to, for lack of a better term, beat the Germans to the punch. Now, the Manhattan Project ends up developing the first atomic bombs, the ones that are dropped on Hiroshima and Nagasaki. These are quite highly debated in terms of, I don't know fully if we understood how devastating they would be. You can get into quite a few heated debates about, does the destruction of those two cities save 1 million lives? How long would the war have persisted in the Pacific? And so on and so forth. But that is a direct consequence and result of this. Now, let's turn to slightly happier things. So an atomic bomb is the result of what we would call a nuclear chain reaction. And in order for a nuclear chain reaction to take place in such a destructive manner as a bomb, you have to have what is called a critical mass. That is, you have to have a minimum amount of the fissile material to get that chain reaction to happen quickly, and to happen and release all of its energy in one bundle. When it comes to nuclear power plants, this is not how the process works. Nuclear power plants are designed to work under the formation and fitting of being relatively controlled. Now, that's not to say that things haven't happened, but the idea is that in a nuclear reactor, there should never be a critical mass of fissile material. And there should be safety protocols in place to help control the extent of the reaction so that it does not happen too quickly. So how does it overall work? Well, again, it is a fission reaction. And what we do is we have the fuel pellets. The uranium are held in what are called fuel rods. The fuel rods are immersed in water. Now, why do we immerse them in water? Well, that's actually a really easy question. We immerse them in water because ultimately we are trying to control where the heat goes. So the energy output gets put into water. Water is then converted into steam, which turns a turbine, which generates electricity. So this is what a nuclear reactor ultimately looks like here. So in the primary building, the reactor building, you have the main reactor itself here. Inside of the main reactor, you've got water surrounding those pumps. You also have what are called control rods here. Control rods are composed of materials that will easily absorb extra neutrons without undergoing fission themselves. So they're usually compounds of boron and some other relatively easy absorbing materials. But what you see is that the heat generated inside of the reactor pushes the hot water into a steam generator. The steam then goes and turns a turbine, which turns a generator. The generator takes the electricity, converts it into on the transformer. And then to keep this from getting too hot, you have a series of pumps that are taking the water out of here, cooling it through the cooling tower, pumping the cool water back into the system. So this big tower that you associate with nuclear power plants, that big cone-shaped Homer Simpson Springfield nuclear power plant image that you have, that's a cooling tower. The stuff that is coming out of it is water, steam. So, and you can see it's pretty far away from the fissile material. So one of the, I guess, misconceptions that is had about nuclear power is that, you know, it's generating tons of carbon dioxide because of all the smoke that's coming out. Well, there's no smoke, it's steam. Oh, well, then the steam must be carrying the radioactive material because after all, it was touching it, right? Well, no, it wasn't. The fuels and fuel rods, the fuel rods are separated from the water. So no, it really is just steam. And so here's a look at a nuclear power plant. And again, you can see here are the cooling towers. And then over here is actually, this looks like the transformer right here. The actual reactor is usually in a dome structure like this. So you can see the dome here. And so the reaction is taking place here in the dome. The electricity is being generated in this building here. And then you've got the cooling towers for the steam there. So how do we control this reaction to keep it from going out of control, to keep it from going bad and being potentially disastrous? Well, if the reaction starts to go out of control, you can drop the control rods into the reaction vessel. Control rods are made out of boron. The boron is a relatively efficient absorber of the neutrons. And so you put those control rods in between the fuel rods. They absorb some of the neutrons. Since there aren't as many neutrons available to keep the reaction going, the reaction slows down. It generates less energy and it slows down the reaction. Most of this work is being done by computers that are programmed to behave based on certain kinds of stimuli, but obviously human interaction has to be a part of that. You have to have the ability to override in emergencies and to adjust to things as they are going. The fuel rods themselves are stored in pool-like containers like these. So here is, you've got a couple of people that are working in the power plant. They're drawing up one of the fuel rods right there. When the fuel rods are spent, that is, they've given up all of their uranium, and now we have those fissible byproducts there. They are quite heavily neutron rich. They are radioactive. And we have to figure out a way to store them properly. This has always been the difficulty of nuclear reactions and nuclear power plants is what do you do with the spent uranium fuel? Thus far, the best solution that we have has been to basically encase it in some sort of underground or under concrete kind of facility and wait for it to cool down. Wait for it to go through enough half-lives that it becomes something that is more close to kind of what we would expect out of normal radioactivity. All right, some top hat questions here. All right, true or false? Nuclear power plants operate exclusively on nuclear fusion. Yeah, absolutely correct. It's not fusion, although that would be the ideal someday. It is actually fission that is the process. Now, nuclear fusion is something that is being worked on. We'll talk about that a little bit more in a second. So we talked about the idea of overcoming Coulombic repulsion. And one of the ways to overcome that repulsion we talked about was temperature. We needed to get to 100 million Kelvin. And the only place where we can really get to 100 million Kelvin is like in the sun. So the idea of doing this on the ground kind of basis using temperature alone is kind of difficult to impossible. But there is another way that we've discovered that we can do it, or at least do something close to it. One of the ideas is, well, what if we accelerate one of the reactant nuclei to such a high velocity that it can pass through the barrier that we would associate by that repulsion? This is the genesis of something called the particle accelerator. Now, there are lots of different particle accelerators out there. In fact, if you look at the periodic table and you get to somewhere around americium 95, what you'll find is that the majority of the atoms that come from everything pretty much past neptunium and plutonium, these are all created through processes similar to this. And so the naming of some of these have a lot to do with where they were discovered. So, for example, berkelium, element number 97, was created in a collider at UC Berkeley. Californium, UC Berkeley. We went on a stage here for a while where a lot of elements were being discovered in multiple places at the same time. And so mendelevium, nobelium, lawrencium, rutherfordium, seaborgium, we start naming them after prominent scientists and physicists. But we get to the last two, tennessine, element number 117, was discovered by a series of scientists working at the University of Tennessee and Oak Ridge Laboratory in Oak Ridge, Tennessee. And oganesson was discovered in Japan. And I forget exactly what oganesson is referring to, but it is based on a Japanese root word. Probably the most famous collider, though, is the Large Hadron Collider. This is the one that exists in the area between Switzerland and France. And it is 100 meters underground. It is gigantic. This is also where a lot of the prominent work has been done for discovering things like the Higgs boson, other subatomic particles, as well as other kinds of work involving large particle acceleration. So here are a couple of pictures of the Large Hadron Collider. On the left here is one of the detectors. This is the Atlas detector. On the right here, we have a picture. So the accelerator is actually curved. I believe it's circular in nature, which allows through centrifugal force creation of a good bit of energy here. Whole thing is 27 kilometers long. So we're talking about a significant portion of real estate here. We're talking about several, rough estimate about 11 or 12 miles. Oh, wait. Yeah. And so in this picture here, you can see that, it does appear to be going straight for long stretches of time, but you can see at the very end of this picture, it is starting to curve here, which does, tell you it is an oval, or at least an oval-like kind of shape here. Now, what kinds of things does this allow us to talk about? Well, because of the ability to throw together some high energy without high temperature, we do have the capability of doing what has been done in stars, and that is fusion. So if I take two light mass nuclei and turn them into a more massive nucleus, like what is seen here, where we have deuterium and tritium coming together to form normal helium and a spare neutron, the net result of this reaction is a considerably large number of mega electron volts. Now, electron volts, it's another unit of energy. I don't remember the conversion from electron volts to joules. But what we do know is that if we compare this amount of energy to the amount of energy that was associated with the fission of the uranium, we're getting almost 12 times the energy. So fusion reactions generate more energy than fission reactions do, which makes the idea of nuclear fusion a lot more lucrative if we can figure out a way to do it safely. And that has been the struggle thus far. We've been able to do it, but we have not figured out a way to do it consistently or safely under, safe kinds of conditions. But that is something that is being worked on. In fact, I read an article earlier this year. There is a company in France, I believe, that is getting pretty close to being able to do some fusion exercises. Now they're still doing it on small scale, but there is a lot of promise, at least according to the article I read, that they would be able to scale it up and potentially, if they could get it to work properly, make it a viable energy alternative. In Europe, there is somewhat of an energy crisis ongoing. They don't have access to nearly the reserves of oil and natural gas that we do. They've resorted to a lot of renewables, which works okay, but they're unable to fully sustain their grids off of wind and solar. So a lot of them have turned to nuclear and have done relatively well with nuclear. But there are obvious problems with nuclear, as we just said, the scaling issue and where to store the byproducts of the fission are significant challenges. So they have been looking for other kinds of solutions. Um, so the biggest hill to overcome here has been the energy barrier for fusion. And again, up until this point, there haven't been a whole lot done with fusion reactors that can generate more energy than it consumes or sustain the reaction for more than a few seconds. So um, this is the article I was referring to. I saw earlier this year. Um, there is a company in France. Again, this is France, France's West fusion reactor, and they were able to maintain a steady loop of burning plasma for just over 1,300 seconds. So we're talking about 22 minutes or so. Um, and so the way that this works is kind of a combination. So you still have to have the hot material. So this is why they're using hot plasma. But what they're doing is they're using hot plasma in combination with kind of the technology of the super collider, where they're able to accelerate it at high speeds in this donut shaped chamber. They're using magnetic fields to help with the acceleration. So are we getting closer? Yes. Um, we are getting closer, but I mean we're still talking about even with this relatively positive news out of France, they say that they are still about 15 years away from anything resembling commercial product. So, and we all know timetables like that. If you're projecting 15 years into the future, 5 years from now, you could easily change that to be 15 more years or 20 more years or whatever. But there is promise there, I guess, is the kind of take home that I want you to walk away with. And so this is more or less a schematic of what they're using in France and in China and in other places. You've got a series of magnets in this donut-shaped kind of configuration. The plasma is being shot through here. It's being accelerated by the magnets themselves. And so the combination of the temperature of the plasma and the energy of the acceleration makes it so that it is possible to overcome the repulsive forces between the nuclei. So last thing that we'll talk about, kind of switching off from trying to do what stars do naturally on their own, is to talk about what stars naturally do instead of us trying to recreate them in a laboratory. Inside of interstellar space, you've got these large gas clouds. Now, some of these gas clouds are just simply nebula that will eventually become stars. Some of them actually are stars themselves. But what we see in a lot of these gas clouds is a whole bunch of hydrogen and a whole bunch of helium. In our star is a helium-producing star. We take hydrogen nuclei, they get fused together, they form helium as a result. And some of the processes that are undertaken to do this start kind of simply. So I take two hydrogen nuclei, smash them together inside of the heat and pressure of a star. We end up getting a deuterium nucleus as well as a positron and a gamma ray. Do that a couple of times. The deuterium can match up with another hydrogen. We get a gamma ray, and we get our first helium nucleus, helium-3. Take a couple of helium-3 nuclei, smash them together, we get the stable helium-4. We also get a ton of energy, and we get a couple of protons back, which can restart the cycle. So as all of this is taking place, it's all happening inside of the star itself. They're being attracted to each other by gravity. We're getting a series of these reactions taking place, and the reactions all generate energy in the process. This energy helps to sustain the temperature of the star. It also helps to sustain the reactions themselves, as well as generate all of that extra energy that comes to us in the form of heat and light, which allows our planet to exist in the first place. So for relatively young stars like our sun, that hydrogen reaction is what dominates. When a star starts to run out of hydrogen, it will start to burn through its helium. Helium fusion takes place in those kinds of stars. This is where we start to see things like, red giant stars, where we're seeing helium being burned more than hydrogen. And the cycle that is generated here is called the CNO cycle, where we can see the formation of carbon and nitrogen and oxygen through the fusion of helium atoms with each other, and then those subsequent atoms being kind of carried through in a cycle here. So carbon 12, which is relatively stable on its own, can be turned into nitrogen 13, nitrogen 13 into carbon 13, carbon 13 into nitrogen 14, also quite stable, nitrogen 14 into oxygen 15, oxygen 15 into nitrogen 15. And we can either continue the cycle, or as some of these heavier nuclei are formed and gain stability, they can kind of take themselves out of the cycle. This is where we get a high percentage of carbon 12. We also see this is a high percentage of nitrogen 14 because those two nuclei are quite stable. All right, last top hat question. And then we are going to call it a semester here. Maybe someday. True or false? Our sun is currently synthesizing helium-4 via nuclear fission. Okay, the statement here is indeed false. We are synthesizing helium-4 in the sun, but fission reactions are not the means of generation. It is, in fact, fusion reactions that are generating our star here. All right, go ahead and get your last participation point. And so this is all for the semester here. That was the last slide. So what we're going to do, let's go ahead and take a 10-minute break. Come back at 9:25. With our last half hour here, I'm going to talk to you a little bit about the exam so that we can spend more time reviewing tomorrow. So 10 minutes, come back, and we'll get started again.